Good day, and you're most welcome to today's session of the CNPS. These Saturday sessions we hold, actually they're held most Saturdays. I personally host them every second Saturday. So this is one of the sessions I'm hosting. I'm Ian Cowan. Today is the 31st of January, 2026. And today I'm delighted to announce that we have Jeff Baugher back again to speak to us. He has spoken to us on a number of occasions before on his mathematical analyses of new fundamental theorems and so on. Today, actually, he'll be talking about, well, this is an unpronounceable CPNAHI. I don't even know if it's an acronym because one would have difficulty pronouncing it, but we'll be enlightened soon about it. It's an update of that, a proposed grand unified theory based on a new fundamental theorem of measurement. Now, so just to go through the spiel, the presentation will propose a new basic equation that gives a proof by contradiction to modern mathematics and the ramifications of using it and natural philosophy to break apart and rearrange not only all of mainstream physics, but both Euclidean and non-Euclidean geometry itself. So, so that's what Jeff will be talking about. Now, I'm just checking. People are coming in, so that's excellent. The link, I've posted the link, the direct link to the green room into the chat because sometimes the generic one doesn't work. But our speaker has got in that way, and he's actually at the moment just getting his slides sorted out. If there are any teething problems, we can deal with those in a moment. I think he's converting it to PDF at the moment. So if you'll bear with me, I shall spend 1 minute, no more, just reminding you that at the beginning of this year, as we did last year in 2025, there was a funding drive launched, basically because the membership dues which come into the CNPS, which are very much appreciated, do not actually cover the running costs. So the shortfall was partly made up by this funding drive last year, and we have exactly the same this year. And I think we've achieved a certain percentage. I don't know, it's probably less than a quarter. I haven't looked at it recently. But so if you forgive me, I'll just play a little video of the president of the CNPS, David Hilster. Let me see now, can I find this? It's very brief. Here it is.
Hello, everyone. I am David D. Hilster, president of the CNPS, and this is our annual fund drive. First, I want to thank all of those who have been paying their annual and monthly memberships through our automatic membership system. It is greatly appreciated. Since 1994, this group has been pioneering support for critical thinkers outside of mainstream science, and we continue to do so through our virtual presence, through our Saturday morning live streams, and our website discussions. Since last year, we have cut our expenses down to something reasonable for our current membership. In 2026, we hope to implement the Discourse Discussion Group as our primary discussion software. Our current website system, in my opinion, is not ideal. We hope to change that. To donate, you can go to fund.naturalphilosophy.org and donate whatever amount that works for you. Your contributions are greatly appreciated. Thank you.
Very well. That's disposed of. So if you could give your attention to that, it would be much appreciated. Now, I'll have to ask our speaker actually for his forgiveness because a few minutes ago I asked him how he pronounced his name. And I think he said to me it's Baugher. There is an alternative, Baugher, which is probably slightly incorrect, which I used. So my apologies if I've done that. Okay. Now, as usual, the format is that I'll bring our speaker up presently, and we might just have a couple of words together. I'll then give him the floor so he can say a few words in introduction, which will, supplement what I've said very briefly. And then we'll give him sort of an uninterrupted period of roughly an hour to speak. It doesn't matter if he spends only 50 minutes or if he wants to go over that by another 15 minutes. That's no problem. And if there are any really urgent matters that you didn't understand a word he said or some concept or something, we could interrupt him. We'd prefer not to do that, but that's an emergency. We can interrupt him. Other than that, we'll wait for the Q&A session after the speaker has terminated his speech. Now, we obviously have people coming in on the social media, on Facebook and YouTube. I see there are 7 comments already in there, but they're probably mainly just good day or something. But if you have any specific question for Jeff, just put @Jeff or question, or Ian, please note, Jeff, question for Jeff, so I don't notice. I don't miss it. And we'll then deal with that afterwards. And then when we've dealt with the specific questions, we shall go to the green room. Now, I see that a number of people have logged into the green room already, and we're hoping that we'll be able to engage in a more detailed chat, a little to and fro with the speaker. So, Jeff, hello again. We've spoken already. Yeah. And forgive me for asking you ad infinitum. It is Baugher, isn't it?
That's how the family pronounces it, but there's different people with the same name around the world. They pronounce it different ways. So it's just how it ended up in mid-America.
Coming maybe from Central Europe, Germany or Holland, and maybe being bowmen originally in the Middle Ages.
Small town in Germany, Niederlingsweiler. Yeah.
Okay, that is all very interesting. Now, so Jeff, shall I put your slides up? Is it sorted out?
Yeah, I think I did. Try the next slide real quick.
No, it's you. You have to advance.
Oh, it's me. That's right. Okay, let me just take a look and see how it turned out. Great.
Perfect, because it was all jumbled before. So you've got
PDFs looks like it sorted it out.
Okay. Yeah.
Thank you, Ian, and thank you for the message on the funding. I do fund the Natural Philosophy Society, and I hope everyone else does too. This is a kind of an update for my research. That acronym is pronounced CIPNI, and it stands for the Calculus, Philosophy, and Notation of what I call axiomatic homogeneous infinitesimals. It's a long name, so I shortened it down to CIPNI to be able to at least differentiate between that and, say, mainstream mathematics. What I'm going to talk about today is something I kind of keep reverse engineering what I'm doing to the very beginning. What I came up with is something called the Fundamental Theorem of Measurement. And that's what I want to talk a little bit about today. So my goal is to make this as simple as I can so that somebody even in high school could understand it. Just to note, I use no AI or large language models or anything to assist in any of this stuff. So I know that's a big thing out there now, but I want to make sure everybody understands that. So my research at the most basic level can think of as 3 areas that say basically the same thing. One of them is to do with philosophy, which is what we consider maybe natural philosophy, geometry, and notation. So all these 3 kind of represent the same thing. They're 3 ways of saying the same thing. So philosophically, you could say, well, I have a length of time of 5 seconds. And with geometry, you might use, say, a line to represent 5 seconds, right? And then you'd have some kind of notation where you say t equals 5, or this thing I have up here, this n times dt. So on one hand, we're using notation to describe something philosophical, a length of time. But what do we mean by that? And we have geometry where we're using this geometry of like lines and stuff to represent this. In CIPNI, though, we have it historically, it views it as what we've always done as being backwards. So you always think of a line and you divide it up maybe an infinite number of times. In CIPNI, you don't divide it up a bunch of times. You start with the little infinitesimal elements, and if you want to make a line, you sum them together. There's a distinction that's pretty important on why I would want to do that. So the goal of CIPNI is I take these 3 little areas here, and what I'm doing is I'm breaking apart everything about mainstream mathematics and seeing if I can place them into the CIPNI framework. And what I mean by that is Euclidean geometry and non-Euclidean, calculus, coordinate systems, tensors, topology, and so eventually get to quantum mechanics and general relativity. One way I like to explain it is that if quantum mechanics and general special relativity were like Italian and French. Sipni would be more like Latin, maybe a basic language. So it's not so much a grand unified theory as it is a grand unified language. It's one language that you can describe both relativity and quantum mechanics in, but you have to change both of those so that they're equal. But when you change them, you don't get what mainstream is telling you. So eventually I end up with the hypothetical argument that I'm not breaking apart mainstream to fit in Sipni, is that mainstream is actually mimicking what I am saying Sipni is showing me. First things first, I need to explain what is a homogeneous infinitesimal, because it's not something you would ever have learned before in any mainstream books, or even in unless you study 16th century or 17th century infinitesimals. So imagine that length is made up of little bitty tiny elements of length, but area is made up of elements of area. Volume is made up of elements of volume. So you can't take elements of length and make area. You cannot take elements of area and make volume. Instead, if I'm going to have length, I've got to use elements of length. If I'm going to use area, I've got to use elements of area. If I got to use volume, I use elements of volume. And on up, we don't have to just have three, but this is the easy way to think of what is a homogeneous infinitesimal. It's a little, what we call infinitesimal element of these. So if I wanted to make a finite length of something, I would have to sum up some elements of length to make a finite sum. The problem is that, well, we'll talk a little bit about how many there are. Now, if I wanted to make up area, I'd have to use a finite number of these elements of area. If I wanted to do finite number of volume, I'd have to sum up these volumes. There's something called Euclid's theory of proportions, which is what this actually is. So it's compatible. If I want to divide area, I can't divide it by elements of length. I have to use elements of area. I have to divide it by the same thing it's made up of. And that's what a homogeneous infinitesimal is at the most basic level. And it's that concept, surprisingly, has never been considered anywhere in the past 400 years that I can find. If you do that, and I have these three little areas here. On the right, we talk about natural philosophy, like what is time? What does time mean to you? What is space? What is energy or energy density, momentum, fields, those type of things? That is a philosophical concept. Geometry is what do we mean by sums, differences, and ratios of these homogeneous infinitesimals. If I want to divide one little segment by another, if I want to add them together, if I want to subtract them, if I want to show how they change a certain way, then that's what I'm calculating, how that geometry changes, and I'm equating that to something philosophically, time, space, energy density. I'm using geometry and equating it to this natural philosophy thing. The third part of this is the notation, the thing on the left. Now, what this is actually saying over here on the far left here, this fundamental theorem of measurement, it's written in what's called set notation. But imagine that if you look at the S there, and you see a dx1, well, you could have a dx1, there's an n there. So if this was just area, I would just have a bunch of elements of area. There'd just be a dx1 plus another dx1 plus another plus another plus another. You add those up and you would get length. That's what this equation is saying. The sum of these is equal length. But what if you have two direction? These are directional infinitesimal magnitudes. Then you get area. I'm just simply summing up little elements of area, little elements of length to get length, little elements of area to get area, and elements of volume to get volume, and so forth. The kicker comes in these two equations at the bottom. If you could take one infinitesimal element and subtract the magnitude from another, if they're the same, you get what's called Euclidean geometry, meaning that if you said there's a point, what you think of as a point between each element, then all the points would be spaced correctly. All of them are equal. How far are they apart? You don't know. You only know if one is equal in distance to the other. But let's just say that your elements of magnitude, those little infinitesimals, are not the same magnitude and they start changing. That's just simply this concept of non-Euclidean geometry. Mind you, this is nothing more than geometry. I'm using notation to represent geometry. Then I'm going to use that geometry to represent something philosophical, like time, space, those type of things. Let me make sure over here in the comments. All right. So this is this fundamental theorem of measurement. It's pretty easy. All I'm doing is summing together elements of length to make length, elements of area to make area, and elements of volume to make volume. So I need to jump in here and say, well, what about all these plots I've ever seen? If you look into proof books and everything spanning the last few hundred years, you might see something like what's on the bottom there, where you have, this is what we call a tangent to a line. So what I want you instead to do is imagine the background is made up of infinitesimal elements of area. They're not squares, okay? So that's the hard part to understand, is they don't have corners, all right? That's a hard little concept, but we'll keep going at it, and I'll show you why. But imagine the background is made up of elements of area, and I project one-dimensional area elements of length onto this background of area. So that shouldn't be too hard to think. What it is that this little one-dimensional thing and when it gets projected onto this background, it inherits the same properties. So all of the points on this line would be evenly spaced, just like the background is made up of evenly magnitudes elements of area. So one-dimensional gets projected onto two. So like this page I'm showing on the left is by somebody named Leonard Euler. And what he's doing here is he's showing proofs through lines, and he did compasses and everything else. What he's actually doing here, according to Sipnai, is he's taking a two-dimensional background and he's projecting one-dimensional elements onto it. So remember how I said Sipnai is backwards. We don't take a line and divide it up many pieces. We're taking these elements first and summing them up, and you get a line. This chart here on the left, you have where on the top with the colors and stuff is what's called a Riemann sum. And below that, you have the definition of what differential geometry likes to call one form. So on the left-hand side, we have what mainstream mathematics talks about is how to integrate. What does integration mean in calculus? So if you take these Riemann sums and you keep taking these little triangles here, not triangles, but the little rectangles, and you keep dividing them up smaller and smaller to infinite, what you end up with is you can calculate how much area is under the curve. In Sipnai, this is a two-dimensional background, and we have projected a one-dimensional line onto it, and what that gives you is a boundary for where you can calculate the number of elements of area that is under this curve. So on the right-hand side is we have a representation of what Sipnai is. Sipnai views these little rectangles, when you get them small enough, views them as like a column of elements of area, right? So in Sipnai, this background is what I would call flat, meaning that the dx and the dy equal each other. But when you change the height of these, you're changing the number. So as your integration goes over further and further, you have more area, right? Well, in Sipnai, you're just summing up more and more elements of area, right? So if I want more area, I just add more elements. And that's what the fundamental theorem of measurement was simply saying, is that area equals area if the number of elements are the same. That's what how Sipnai views it. So this is kind of like a what I would call everybody remember what the Rosetta Stone is, where you have different languages saying the same thing. So on the top left, we have a Riemann sum, which is taking these little rectangles and going down to just little bitty elements of area as a rectangle. And then we have what's called a one form, which switches over to differential geometry, where they call a one form this column here, or I'm not sure if they have a better way of saying it. Where in Sipnai, we're looking at a column of elements of area. The more elements you add up, the more your area goes up. And the reason is because the dx and the dy are the same magnitude, but the height of it, I'm using this little n over here. If you look where it says in the middle on the green on the right, it says y equals f of x. That's a functional notation which occurred later on in the development of calculus. But we say that height of this column is n times dy. The n, you could think of the n as the number. It's actually the cardinality of this set of elements. That equals the height, and the width of it is dx. So what you're doing is you're summing up columns of these elements, and as you sum up each column, you are increasing the number of elements that are there. So how does this work with a derivative? Well, you've seen the notation. If you've ever seen the notation dy over dx, taking the slope of the line, the tangent. Instead, in Sipnai, what we're doing is we are counting the number, the change in the number of elements. So over on the right-hand side, you might see a proof in a book where they talk about delta y is the change along the y curve and dy, but the dy and the dx are not the same thing here. What you're looking at is you're looking at the change in the height of the number of elements of y for every element of dx. So I'm looking at how does the dx change? If the numbers are the same, if each column is the same height, that's like the derivative of a constant. you're not looking at any change because then there's no change in the number of the elements and high. So this is one of the notational differences between SIP-NI and mainstream mathematics, is that you have to understand is that if you're looking at a constant magnitude of these elements and everything, you're actually changing the number of them. And that is what a derivative is. You're looking at the change in the number of elements in this column. So if an elements are the same size, that means one line is longer than the other if it has a higher number of elements of length. One area is greater than another area if it has a higher number of elements of area, and one volume is greater than another volume if there's a higher number of elements of volume. This is why the fundamental theorem of measurement is important, is that what do we mean when you say the difference between size? Are we looking at the magnitude of the elements themselves, or are we looking at the number of them? There are two different ways to think of a change in size. So that's a problem that we have, is that in mainstream mathematics, they don't teach this infinitesimal concept anymore. You might see it in engineering and some other things, but if you get into just mathematics and everything, dx has been rooted out. So the problem is sometimes you'll read into old papers and small papers by historians, and they say that dx has different definitions. It is sometimes defined as the smallest difference between two real numbers, or it is the smallest real number. So imagine that I have dx as a small real number. Well, in mainstream mathematics, dx is even smaller real number. So it goes to zero faster. And this is the logic they use. They don't look at it as a element of length or dx as an element of area or anything. They look at it as simply a way to multiply against each other. So if dx is something small, dx times dx is even smaller than that. And sometimes they'll say dx is equal to 0. So there's all of these definitions, and they're not consistent across the papers and stuff. And in SIP-NI, it's fairly simple. dx would be an infinitesimal element of length. dx would be an infinitesimal element of area. So on the left-hand side is some of the things that I've found in mainstream mathematics about what you can multiply against this dx. Over on the right-hand side is the way SIP-NI would write it. The problem is that there are some concepts in SIP-NI that have no equivalent in mainstream mathematics. So if you look at the bottom where I say dx is an infinitesimal magnitude, or the sum of dx is a summation of magnitudes, you don't see that, especially the summation notation. You'll never see that in mainstream mathematics. If I'm comparing the differences between the magnitude of two elements, it's dx minus dx equals delta dx, in the middle on the green side on the right, that is a change in the infinitesimal magnitudes. That concept does not exist in mainstream mathematics. And it should, because that is very similar to whenever they talk about coordinate systems where the points are changing distance. So in SIP-NI, we're keeping track of the number of elements. That's what the cardinality is. Whereas in mainstream mathematics, they like to think of coordinate systems, and they talk about the number of points. And there's a flaw with doing it the way the mainstream mathematics does. So delta n dx, that's a change in the cardinality of magnitudes. Just like where I talked about we had two columns of area and we were changing the number, that delta n dx does not exist in mainstream mathematics. Even though I can write it out and I could write a proof, because this doesn't exist in mainstream mathematics, it makes it difficult to even get a paper into past a journal editor. So there is somebody on here said, what is the purpose of all this? What is it meant to prove? Why do we even care? Why do you even care about learning about dx at all? I mean, especially from natural philosophy. The point of learning about dx and this mathematics and stuff is to understand the difference between an element of volume as a coordinate system, as in general, I'll tell you, or an element of volume as the density of a fluid. So you have to know philosophically, what are we talking about? Are we talking about a coordinate system here, or are we talking about the density of a fluid? And that's the problem with the cosmological constant, is that general relativity originally said, hey, it's a coordinate system. That's what we're doing, is we're looking at a coordinate system change. Whereas what SIP-NI says, no, this is an element of volume. We're looking at the change in the density and the strain of a perfect fluid. So there's a distinction, a philosophical distinction between a coordinate system. So you imagine a three-dimensional coordinate system, all right? It doesn't take much concept to add a fourth dimension onto it and say, well, these are all coordinate systems changing. Or it is an element of volume here, and we're saying, no, this is not a three-dimensional coordinate system. It's an element of volume, and when this changes and everything, we're looking at the strain of a fluid. Well, what about the fourth dimension? Well, that's when you have to get into philosophical concept of what does dx mean? Is it a fluid that changes and stretches and everything, and the rate that something clock ticks or in that fluid based on the strain changes. So you can see they would look a lot alike, but you philosophically have to understand what we're talking about mathematically. Is it a coordinate system, or is it an element of volume? Is it a space and time, or are we looking at a perfect fluid that's stretching around elastic material? So without having a basic fundamental thing at the bottom here, you have to understand where we started from. And that's what I'm saying with this infinitesimal concept, is why we're starting from here, is because I need to know the difference between a coordinate system and an element of volume. Is it space and time changing, or is it a fluid that's an elastic material that's being stretched, and the vibrational rates in this fluid as it stretches and strains and everything changes where it's based on it, where it's at in it. So that's the whole purpose of even bothering to try this, is to understand the difference between why Euclidean, non-Euclidean geometry gets, we create differential equations out of all of this. All of Newton's laws of physics, gravity, I'm talking about even, Newton's laws of motion and everything, are all based on calculus. So that's the reason we want to understand this, is where did we start from? Where are the flaws at? If you rebuild it this way, then maybe we can get to something that's more logically consistent. There are certain paradoxes that can be solved this way that cannot be solved with mainstream mathematics. There's this thing called the Torricelli paradox. So on the left-hand side, if you see this rectangle here, you see where the areas of the triangles are actually equal on the top and the bottom. See where it says E, F, and D, and E, G, D. Those triangles there are equal area. Well, so are the other parts on it. The top where it have along AB and along BC, those are equal too. Well, if you smash those lines, if you take E up to B, or and those become very thin, the problem is that they're not the same length, but they have the same amount of area in them. You can solve that with using SIPNI, with these elements of area, because even though they're not the same height or length, they have the same area because the infinitesimals aren't the same magnitude. You can read about, I'll give you a link to a paper so that you'll be able to look at it better. And even if you don't like what I'm doing here, the problem is what I want to do is debunk what's called topology, and even how we develop the laws of physics through calculus. So let's just say that for some reason you don't like it. At least you can use this to say, well, you know what? There are things in modern mathematics that they've never thought of before. They've never tried homogeneous infinitesimals in the last 400 years. There are things called Gaussian curvature. Why do we care about, why does somebody in natural philosophy care about Gaussian curvature? Because they look at it as a surface, and this surface can be flat or it can bow a certain way. Well, guess what? The same thing can be thought of as an elastic material stretching and stuff. So I can make an elastic material change and stretch with these homogeneous infinitesimals as what they're calling Gaussian curvature. So the surface of this thing that they're talking about, these surfaces and stuff, they're talking about bending and deforming and stuff, could be the same thing you thought about as an elastic material stretching and stuff. You cannot write equations for this with modern mathematics for this bending and stretching and stuff. You have to have elements of length, volume, and area and volume and stuff to be able to do this. So it's been missing from our mathematics. So basically, ether theory went out of vogue because there was no way to describe the ether well. That's what the elements of volume are here for, is so that we now have a mathematical language that I'm saying to describe ether, and you can falsify how they're doing it with general relativity. So you can look in mainstream mathematics where they talk about taking this plane and moving it around over this surface and everything. And all they're doing there is using realistically elements of area on the surface of elements of volume. This thing at the bottom, they talk about rays coming out of these surfaces and stuff. These are just elements of volume that are being used. So for every analogy they have in mainstream mathematics, SIPNI should be able to have its own analogy and have it logically better. This is just a description. Again, when we take we have to have some type of notation. So if delta x equals length, all dx is when you start dividing up this delta x an infinite number of times, what you end up with is this equation n times dx. And that's if you do it the mainstream way. I'm dividing a line up many, many times, and I have n number of them. The problem is that this n number has not been understood by mainstream mathematics. And I can find all this stuff in the books as you start searching back. You take this one equation for the fundamental theorem of measurement, If you take that concept and you start looking back through the history books, what you'll find is you'll find flaws in them. So they might write A equals B, whereas in SIPNI at the bottom there, I would say, well, the length of A is N times A dx. The length of B is NB times dx. It doesn't matter just the magnitude of the infinitesimal. It's how many of them are there, the cardinality. And so there's a big thing in general relativity about scale factors, right? So if you look up scale factors on general relativity and everything, you might see there are some what you would call some YouTube videos out there where they will describe scale factors. Well, in SIPNI, there are two types of scale factors. I can either scale the number like in a line. So if I want a line to be twice as long, I can say, well, there's twice as many elements in that length. This is the same thing as what's called a Euclidean scale factor. So I'm making the line twice as big if I double the number. Pretty simple concept. It's just algebra. But the same thing happens if I scale the magnitude of the infinitesimal. If it's twice as big, my line is twice as big. This concept of this scale factor, I can directly equate to what's called a metric within general relativity. I'm going to skip over these other slides because I'm just going through equations and stuff, talking about area and stuff. And it might be a little more confusing than we need for this presentation. So imagine you have area. If I want to add two areas together and they're the same area, there's two ways to add them together. I can say I've doubled the number of elements in there, or I've doubled each of the magnitudes of each of the elements of area. I end up with two areas that are the same. One of them has elements that are twice as big, and one of them has elements that are twice the number. So that's a concept for scaling that does not exist in mainstream mathematics. I'm going to skip through here. So what I'm saying is SIPNI has its way of looking at things. Mainstream mathematics does. If you debunk the way mainstream mathematics does, what you end up with is something that looks very conducive for ether theory. So a zero form in mainstream geometry would be a column of elements. A one form is this thing called a column of area. Two form is a column of elements of volume. So length, area, or volume as a column. Zero form, one form, two forms and stuff. A circle, what we think of as a circle, is just a line drawn around where you can draw radiuses of the lines coming out of it. A one sphere is something that they kind of call it a circle in differential geometry. But in SIPNI, it's actually just wedges of these lines coming out where the infinitesimals get bigger. I'll give you a link to a paper and stuff so that you can have a better idea of it. The sad thing is that if you want to be really good at natural philosophy, I think, not just the philosophical part, but why does mainstream believe what they believe? What is the compelling reasoning behind all of that? If you take SIPNI and you start examining what the assumptions were and everything, you can understand why people would say, well, this is why calculus works, and this is why differential geometry works and everything. But if you decide to go with infinitesimals, all of a sudden you start to see that, well, it's not unique to what you're saying. This is to me is a better way of organizing it. The problem is when you get to the philosophical part of what do you call energy density and momentum and everything, and you start comparing that to the old ether theories, you're like, well, this works out a lot better than we thought. And as a matter of fact, that's what general relativity is trying to do right now. When they call the cosmological constant the density of the vacuum ether, the vacuum energy density, what they're actually saying is it's a perfect fluid out there, just like ether, but it's supposed to exist out there miraculously. Whereas SIPNI says, well, yeah, we model everything as a perfect fluid, and the changes in the density and the strain of this thing is what we call energy density. You're right back to ether theory. So before it was all supposed to be a coordinate system that changed points and everything. But now you're back with having elements of volume and everything, the strain of them changes and stuff, and you're right back to an ether theory here in 2026. So this again is the equation and the three portions of SIPNI. You have on the left, you have the equation itself. In the middle, you have what I talk about, the calculus of geometry. How do we add things together? How do we find ratios of things? But you're actually looking at elements of geometry to find all these things. And on the right is natural philosophy. What do we mean by time, space, energy, momentum? These are all three different ways of saying the same thing. So again, it was asked, why do we care about all this geometry and stuff? Well, originally in general relativity, you had an equation with two sides. It's called the Einstein field equation. You had this part on the left-hand side was describe curvature of space and time, And on the right-hand side was energy, density, and momentum. And that's the way you would hear it described, is that energy, density, and momentum curve space and time. Well, space and time is supposed to be a coordinate system, and the points all change and stuff. And energy and momentum was modeled after a perfect fluid. They said, hey, these things are exactly the same thing. When you curve this space and time and stuff, this coordinate system, and these things change and everything, it's because you have this energy, density, and momentum over here. That is the same thing as that. That is original general relativity. Now what we have instead is they've tacked on, well, I say now, but it's always been there, this lambda g mu nu. Understand there is no r next to it, no Ricci tensor right next to this g mu nu. That g mu nu was supposed to be a measurement of a way to see whether or not the coordinate system is changing. Well, now what they're saying is, nope, the coordinate system itself must be a perfect fluid. They don't like that, and it doesn't make sense, because how can I have a coordinate system that changes and everything, but the coordinate system itself is a perfect fluid? This is why the equation no longer makes sense. And that's the whole point of having this, is that if I have a density and pressure of a perfect fluid, that is the cosmological constant. So we're right back to ether theory. This is a slide I was just saying that the reason that you will not see anybody, mathematicians, studying infinitesimals today and stuff is because of what's called real analysis. Real analysis is taken over. So just like coordinate systems and general relativity is taken over from ether theory, real analysis has taken over from infinitesimals and stuff. So this is why you'll no longer find anything in a university or setting and stuff to study infinitesimals as part of a university course. There is something called non-standard analysis, but it has its own flaws. It's tried to bring back infinitesimals, but in itself is flawed also. I'm gonna skip over the scale factors and stuff, because I think it's gonna be a little bit, I think the math is too heavy for most people. But if you want this slides and stuff, you can let me know and I will give you the slides. The whole point of this research was born out of the desire to understand the cosmological constant problems. You have to reverse engineer the thought process that came up with general relativity. And when you come down to this lambda g mu nu, this thing here, this top left, if you break it down to its constituent components, all you're going to get is what's called a scale factor and an infinitesimal. So if you keep reversing engineering it down, what you're going to end up with is some type of this cosmological constant, and you need to philosophically equate this thing. All of a sudden, you're looking at the density of a perfect fluid that we're representing as space. And now you're right back to ether theory. And then that means that you need to reverse everything, the whole process, to come out with an equation that can describe the ether, but you have to do it with homogeneous infinitesimals, according to this. Future research I'm going to work on this year is to write a whole book, because some of the questions I see here are just like, well, why do we even care about this? Why would I care about learning about this? Well, the whole point of it is to go all the way back to the very beginning, to where we started at, and to see how was Euclidean, non-Euclidean geometry developed? How was all of this stuff developed? And when you do that, you start finding mistakes. So things like constants of integration, all of these things, there are different ways of looking at these which are more logically correct, where you don't end up with the paradoxes of singularities and these types of things. So that's the whole point of this, is that there are no other mathematicians that are working in this because they have cognitive bias. They're all working with real analysis. They're all working with metric spaces and this stuff. But if you're not willing to go back to the very beginning and find out what was wrong, you can never get to this point. On this slide here, you can see the VIXRA abstracts. The top one is more mathematical, or the bottom one is more mathematical. Well, I should say the top one is more mathematical. The bottom one is has also the philosophy of what you would do with this. So I'm going to go ahead and call that as the end of this presentation here. Ian, you still with me? Let me take a look at the questions.
I have to bring myself back. Yes. No, thanks very much, because you took me by surprise there. But that's fine. It's 20 minutes to the hour. So that's a lot of very interesting information, very clear slides, but you've gone through it in at some speed. There have been some questions here.
Yeah.
Perhaps By the way, Jeff, shall we leave your slides up for the moment, or shall we take them
Yes.
down?
No, leave the slides up. That way,
Okay.
if there's anything in here I want to go back to.
Okay.
So
Yeah.
the question is, I guess I have for the group is, the problem is, this is a different way of mathematically looking at something. And historically, these have not fared very well. So that's why I'm trying to find a way for people to understand this graphically, just like we did with because people kind of understand when you're learning calculus, and you're in calculus 101, you learn Riemann sums, these things here. But in natural philosophy, we never really ask, why do we care about Riemann sums? Let me go back to it. This thing up here, this top left, where it has the blue, red, green, and yellow. This is off of Wikipedia for Riemann sums. This is how calculus is explained, is how do we calculate the area underneath this line? And some people will say, well, why do we care about this? Well, the reason you care is when we write physical equations, like say if we're looking at the gradient of a Newtonian gravitational field, this is precisely what you're doing, except you're doing a three-dimensional system, a three-dimensional coordinate system. Well, so that's the hard part, is not understanding that when Newton built stuff like his gravitational equation, and he used calculus to do it, and we have this thing called the gravitational potential, and we're looking at the change of this potential and stuff, that what you're actually doing is what is on this top left. If you take the philosophy out of it and everything, this is what you're doing when you find the change in the slope of this of what we call the gravitational potential, and you get a force vector out of it. This geometrically is what you're actually doing. We may think of it as Newton's law, and we write that out and everything, but where it came from is what's on the top left. This is the most basic way to explain what a differential equation is. So so I'm going back into studying not just the laws of physics and everything. Where did these laws of physics come from? How do I calculate the gradient of a gravitational potential, or of any potential? So this is what we're looking at, is what is our assumptions here? And that's the problem, is that the reason this is so complicated is that most people don't realize this is where it started from. And what I'm doing is I'm looking at our assumptions of where we started from a gravitational potential. The part on the bottom where that says definition 3.11, this is the start of what's called differential geometry. And this is where geometers start, when they start talking about all of this bending and moving around. They're using this argument to say this is how coordinate systems work. Whereas a natural philosopher might say, well, no, how do we know this isn't an elastic material that's bending? How do I know I'm representing a coordinate system, or how do I know I'm representing an elastic material that's bending? If you frame it in that way, and you have this tool of Sipni to aid you along, you counteract a lot of arguments that came out for relativity.
So if I could just go back for a second before we get to the questions, Jeff, you've alluded to later works by people like Riemann or Euler and so on. But the question, if it's not an unfair question, is this. It occurred to me that you seem to be advancing on some of the fundamentals of the mathematical treatment. Forget about physics just for the moment.
Okay, yeah.
So could you speculate, is this not an unfair question, could you speculate that if you put these principles to the developers of calculus, say to Newton or to Leibniz, do you think that they would be in favor of those, or would one be more amenable to your ideas than the other?
I think if you showed this diagram here, and I explained it to Leibniz and Newton, we would have never had calculus like we have it now. I believe that both so this problem on the left was not unfamiliar to either Leibniz nor Newton, this one on the left, but they were not able to explain it in a succinct way. So it just got pushed aside because calculus works so well. But if I explained Sipni to them and said, hey, we're changing these magnitude stuff, both Leibniz and Newton, I believe, would have went, oh, now we get it. Okay, this is why calculus actually works. And what would have happened, and then Riemann and all these people who understood this, how Gauss and stuff, how to understood bending and deformations and stuff, would have went back and said, oh, all right, we're actually just changing magnitudes of all these things. There's a simpler explanation if you think of it this certain way. So yes, I believe all of these mathematicians that if you went in the past and you explained it this way, they all would have agreed with me. And I believe that their proofs would have started with what I'm starting here with that fundamental theorem of measurement or some form of it.
So it appears to be more concerned with the differential aspect of the calculus. So again, if I could just speculate a little more just before getting to the questions, if you go right back to, say, Archimedes, who was concerned with, the integration of the areas on the curve and so on, would you think that would change that concept in any way?
No, I think what would have happened, there would have been, because because the problem with differentiation, the way we look at it now, is that we have to map a one-dimensional segment onto two-dimensional elements. I believe that during the 17th century, they figured this out, that when you're integrating the area under the curve and everything, you've got this problem of what does this mean and stuff. So there's no problem with taking a plot and drawing lines through it with points and everything, as long as you don't involve infinitesimals. So it's still valid. It's still very useful to take a plot and draw lines through it with points and everything. That in itself will give you correct answers, as long as you don't put infinitesimals with it. Once you start putting infinitesimals and you don't use homogeneous ones, then you're going to start getting paradoxes, geometrical paradoxes in it. That's actually what non-Euclidean geometry is an attempt to solve that, but through a different way. But you still don't realize what the fundamentally underlying reason for it is, and that's why you still get paradoxes with non-Euclidean geometry. So the whole reasoning behind this is that the cosmological constant is considered a constant of integration. What the heck does that even mean in a geometrical sense? In SIP-9, there's two different constants of integration. There's one that says, I don't know, I'm looking at the change in the height of these columns, but I don't know what the actual number of them is. And in the magnitudes I don't know what the actual magnitude is. I just know the differences in the size of them. So they both go back to this concept of not knowing what the absolute magnitude of numbers or the absolute magnitude of the size of this thing is. But that's what a constant of integration is. And that's, if you look at it in the way I'm doing it, I believe that all of these mathematicians and philosophers and stuff would have done it this way. So all of the points, Archimedes and stuff, with drawing the lines and everything was great, as long as you didn't introduce the infinitesimal concept, which it came about on the Italian peninsula. So Galileo, Torricelli here, all of these other people that were working on this infinitesimal concept, it got shut down in Italy, which is why England and Germany kind of took over for calculus. They were ahead of the curve at one time, but there's a lot of history with the Catholic Church and stuff on infinitesimals with Galileo and stuff.
Oh, okay. Well, there's some questions here which are maybe concerned with the application to physics, and there's some little discussion about magnetohydrodynamics in particular. A very general question has come in here. How would this describe magnetohydrodynamics?
The problem is that I don't I know what magnetohydrodynamics are, but I have not worked out stuff like Maxwell's equations and stuff. So I don't have those transferred from SIP-9 to those. I was trying to start out with the mathematics and stuff. So the problem is that when I look at these equations and I look at, what it is, I view general relativity as a bad ether theory. It still describes somewhat and stuff, but to me, it's not a changing coordinate system. It's a change and stretching and stuff. I don't look at things as flowing, like a huge flow, like water fluid and turbulence and stuff. Instead, I look at it as a wave passing through an elastic medium. So there's not a huge flow of stuff and everything. So if you're talking about magnetohydrodynamics, that's a complicated equation. And this stuff I'm doing is extremely simple. It's at the beginning. So I wouldn't have an answer for that.
Okay.
Let's see if there's anything else.
Yeah. I don't know why Jim Morrison has raised the application, or is this related to Zeno's paradox?
It very much is.
It is, okay.
Yep. So what Zeno's paradox and stuff, and you can also talk about the tortoise and the hare analogy and stuff about. So the whole concept of that was, if you had two of them If you had a tortoise racing and you had a rabbit racing and they start at the end, they would say that, well, if you can always divide up time more and more and more, the rabbit would never catch the tortoise because you can always divide up time more and more and stuff. And that's a problem. The whole analogy breaks apart on the Zeno's paradox because you have to look at the sum of the elements, the number of them and stuff. So in this context, and this would solve Zeno's paradox because they are both at the exact same distance even though we're taking magnitudes of time, we're saying top. So the elements of time are constant, right? As what we think as what we'd use in infinitesimal dt. But in order for them to be equal and everything, you have to look at also at the elements of space. So the elements of space aren't the same, but the number of when you add them up together and everything, you would say, well, they both cross the same distance and everything, even though the magnitudes of the elements of space aren't the same and the numbers aren't, it still sum together to equal the same. So it's a hard way to describe it verbally. I'd have to draw it out. I did write it out one time how to describe Zeno's paradox, but it's very much aligned with Zeno's paradox and all of the infinitesimal paradoxes, which is what Zeno's is about.
Right. And actually, we might have some discussion later on with the green room people, because I think James Keane has raised this question again about discrete space versus continuous, because that might have been the classical way of resolving this Zeno's paradox, where you're describing things, but in the limit, it became a continuous thing.
Right. I would say so. Here's what that's a good subject is that I look at this as Sipnite as a language. Just like, you have different languages to describe snow and stuff. This is a language which I believe is the best language we have for describing our universe. I don't actually believe our universe is discrete. This might be discrete, and it is discrete and stuff, but this is the best language we have for describing what I would call ether theory. So although this is discrete, we can use these changes and stuff. To me, philosophically, I describe time and space through periodic events. So, is time for me, time is it a rotation of a planet? Is it a vibration of a cesium atom? So these are temporal events, temporal periodic events. And to me, that's when we talk, I know people don't like the word time dilation, but what I look at it is there are different vibrational rates for things depending where they're at in the gravitational field. To me, that is what time dilation is that things vibrate at different rates and everything in a gravitational field. And that's what this would show. And space contractions would be changes in wavelength of stuff. So things are not the same size depending on where they're at in this gravitational field, which is described using some modulus infinitesimals. So it's periodicity, but we're changing the size of the periodic events. And I'm using this to describe that change, but I don't believe that space itself is discrete. Does that help?
Yeah, I think that helps, and it'll give us something to start a conversation on this later on, I'm sure. But so just a couple more before we get to the more detailed conversation. Green Science has said, I don't know, he's very critical. Finite elements are, I don't know what TG, WTG. All this infinitesimal stuff is like going down a blind alley and falling into an open sewer. So,
well, I can understand the sentiment, but the problem is that I had been told that everything that could be tried had been tried, especially with infinitesimal stuff. And what I found out is that is not true. Even if you look at this graphic that I'm showing you here, this puzzle even puzzled Newton and Leibniz and everything. And I'm not saying I'm that much smarter as them, but I've got 400 years of hindsight to look back at what everybody else has done. And what I can tell you is that is not true. Infinitesimals have been abandoned. So what I mean by that is that they were abandoned by mathematics because nobody could figure out them, because it was a blind alley. Nobody had a good way of describing these. So that's what this whole fundamental theorem of measurement is. It is a new way of looking at infinitesimals that solve 400-year-old problems that have never been looked at before this way. And that's simply what it is. Even if I'm wrong, which, anybody can be wrong and everything, I cannot figure out a way that I am wrong. I've looked at it from all different angles and stuff. And if we are really this wrong about how we describe our universe with mainstream mathematics, and we don't find a different way to look at it and stuff, I think we're just going to have worse and worse paradoxes. I would rather go back to the very basics and see what our fundamental assumptions are and stuff. And even if this was ended up not being correct, I would want to know why that is. So that's why I'm trying to promote this, is that I can find no reasons for this that I'm wrong. So he's saying it's a blind alley and stuff. I'm saying, well, where we're at right now in mainstream physics is a blind alley. We keep coming up with new fields. And I mean, I know I'm preaching to the choir here. I believe everybody here agrees with it. And I understand I did not start out as an etherist or anything. You know, I really had no interest in any of the stuff because I figured it was way over my head. I understand infinitesimals pretty well. But I also understand it's like at some point I'm being told that there's this perfect fluids that are out in space is supposed to be this dark energy. And you do the research, you say, well, what happened? Why did we do away with ether theory? When you start looking at the mathematics and the geometry, that's where I'm like, wait a second, there's something wrong here that's never been found before. So while somebody says might say it's a blind alley, I say, how would you know if you haven't ever tried it?
Have you had different responses from mathematicians as against physicists, Jeff?
I have for basic mathematicians, ones that teach stuff like calculus and everything. People that want to know what calculus is. If you've had a background in this Riemann sums and you're teaching all these different types of integration and stuff like that, yes, I've had people who I had somebody who was very bothered by it. He said, how am I supposed to teach calculus now, knowing what you've showed, and saying that, you know, this, it's, you know, it's a bit mind-blowing to say, well, there's a different way of looking at just even simple calculus, finding the area under the curves and everything. They realize it's like, wow, everything I have been told and stuff may be logically flawed, and this may be a logically correct way of doing it. So I actually have been thinking about trying to maybe coordinate with Indian mathematicians, because I think they're not quite as married to relativity, and they're willing to look at other things and stuff. And, you know, and India has a good tradition of mathematics and stuff. So I've been thinking about trying that. So I need to write a book about all this where I can explain it from the beginning and explain why do we even care? Why should somebody even take the time and effort to look at this stuff, especially if you care about natural philosophy? Well, because with natural philosophy, if you have an ether and that's what you think that there actually is an ether, you think it's a good model. This to me is to say, well, this is, if you're going to have an ether, you have to have a choice between, is there an ether or is there a coordinate system? And what's the distinctions between the two? In general relativity, they have basis vectors and coordinate system stuff. You need to understand the difference between what those are and what this is, and be able to have those in your head and stuff to sit there and start building up in comparisons and everything. So my intention is for this to completely replace everything that we know about modern physics, so that we start at the beginning. That's a tall order. So I'm trying to enlist people just for the basics of it to get this going.
So there might be two separate prongs working in parallel indicated, Jeff. One would be the very, enthusiastic aspect that you talk about, demolishing the whole of modern physics and by these methods and so on. And that's going to result in a lot of opposition, obviously. But another parallel strain might be to put it to pure mathematicians without any cognizance of its application to physics, just as a tool which perhaps one could use. And one might be able to get a little more leeway there, without all the prejudice coming up immediately.
Right. And that's why, so I have one of my papers is specifically just about geometry and not to deal anything with the philosophical part of it. So let's just leave natural philosophy, at least leave time and space and ether theories, right, energy density, all that out of it. And so I went solely with a mathematical presentation of it. The problem is that this equation, let me go back to it. This equation right here on the left, this is written in set theory. This type of equation, even though I'm using set theory notation, has never been proposed before, where I'm simply summing up lengths of elements of length and elements of area and stuff, which is kind of surprising when you think about it. I think I do have a good shot of finding people that are can understand the ramifications of the left, and can understand, what does it even mean, and simply from a mathematical background and geometrical background. The problem I have is I need to get better at explaining this and everything, because when you submit papers to journals, it's a one-shot thing. There's only so many journals that would publish something like this, and if they reject it, you can't resubmit it. So I need to write this out better and explain it better and stuff before I submit it to any more journals. Most papers are rejected, but something like this, I would hate. It stinks because if word gets around, because I found out some of the referees, or not the referees, but the editors and stuff, know other editors at other journals, and if they know your name and somebody says, "Hey, I got this weird paper," yeah, we rejected it. I'm sure they're going to reject it too. I've only submitted to 3 mathematical journals, which got it rejected, but they don't say why. I did get it through one journal past an editor, but it was a physics journal, and the physicist said the mathematics were too speculative. Which I can understand that kind of sentiment and stuff. It's a tall learning curve to have to do this, to say, hey.
But you have succeeded in some publication, have you?
No, I have not. Not in a peer reviewed, because I got to the editor stage and stuff, but this has not made it into a mainstream. And there's plenty of journals out there that say they will publish stuff and everything, but I'm going for more major journals, because there's no reason this equation on the left should not be publishable by a mainstream mathematics journal. So even forget about physics and forget about everything else. The equation on the left is nothing more than geometry, and there's no reason that the question is, what do you mean? What's a proof? And even mathematicians argue about what a proof is and stuff. So I'm starting out with this primitive notions of these lengths and stuff. And they're like, well, we've never heard of this, so we're not even going to bother publishing it. So there is going to be a way, somebody out there that will take this on. But it might take a few years. So we'll see how it works out.
We got some information recently from another presenter, Joe Sorge, actually. And he got a paper published looking at some physical aspects of motion and so on in IOP journal, I think it was. But he said it was a double blind system where the reviewer did not know who the composer was. And,
yes, I saw that.
Did you see that? Yeah.
Yes, I did. I haven't read his paper yet. But congratulations to him. Any I guess headway that natural philosophy can make, because I do believe that natural philosophy is the way forward. I think the way we're going down now is that blind alley where we're talking about. I think relativity itself is a complete misunderstanding of geometry and philosophy. So congratulations to him. So I might try to find that same journal. I know it's a European journal, and I might try to go, or at least find a journal that's double blind. I think I would have better luck, just like maybe he did.
Okay. So just before we get on to the green room, this sermon was talking about levels, and I think he means magnitudes by that.
Let's see if it's in there. Is that what he meant? Magnitudes?
He says yes. Levels equals magnitudes. Do they come in?
If he's talking about like quantum mechanic levels or quantum electrodynamic levels, not right. I see what he's talking about. Like, because in a atom and stuff, we don't talk about where a electron is. You talk about probabilities are they are, and you have different energy levels of all the shells and stuff. So that is something you would build up to based on this. So this, you would have to use this to describe what we find in nature. But what this should do is should give you a way of describing all of these levels and finding a pattern to them using this way, using SIPNI. So eventually, if it would have to include levels. If it's going to be of any use, you would have to eventually include magnitudes and levels. So yes, definitely. But as of right now, no, I have not gotten that far.
Okay. Well, we're more than halfway through the talk, so you're going to have to forgive me for asking a very, very basic question, but I think it may help a lot of us here who've just forgotten about it. Could you just remind us again what exactly SIPNI stands for?
Okay, so let me go back to the very beginning. and I know I rush through these things. I talk fast, unfortunately. So SIPNI is an acronym. See in the top left where all the little lines
yes.
are? So it's a long term for these three concepts, the calculus, philosophy, and notation of these axiomatic homogeneous infinitesimals. What do we consider length? What is area? What is volume? And all this stuff. So when calculus means is that how do we, if you wanted to calculate how much energy is within an atom and stuff, you would say, well, we could find out what the energy density is, and we know what that is, and we calculate it over the volume and stuff. And you might integrate this stuff. So that's the way that we think of it, of saying, I want to find out what the total energy of this particle is. I would find out what the energy density is, just a simple thing, that volume, and I'd find out what the total energy is. So that is the way we think of it. What this does is it breaks all of that apart and says, are we using the right assumptions for everything? When we say volume, we tend to think of spatial volume. This is how humans think. When we drew a line and stuff, you say, well, this is the length of if I draw a line on a piece of paper and I say, this is the side of my field out there, and it's 10 meters long. You know, the line itself isn't really 10 meters. We're using it as a language to represent something else. So that's the same thing. That's the same thing that I'm talking about here. I'm using calculus, a line here, to represent something else. That's philosophical. I'm using it to represent something else. Well, I have to look at the notation for this. Are we using the right viewpoint for all three of these to build a coherent view of the universe we live in? And this is why when we're in the blind alley we're at now, where they have this cosmological constant, it's like we've been led down this path now of coordinate systems and energy density and curvature of space and time and everything. We've been down this alley, and we now have this term that no longer makes any philosophical sense to not us, but not even mainstream mathematics. They don't know what to do with it. They're like, something's wrong. I've seen many quotes with this. People aren't sure why theoretical cosmologists don't lose sleep at night, because if this thing were what we thought it was, the universe wouldn't exist, and we're here. So that's why I think it's up to natural philosophy to go all the way back and look at the assumptions for everything. So that's why there are three terms in here. And to me, there are three separate things. There's the calculus of axiomatic homogeneous infinitesimals, meaning adding, summing together lines, areas, volumes and stuff, ratios and stuff. And the notation, well, do I write a line with A equals 5, or do I say there's a number of infinitesimal elements in this line? So how do we write this out as notation? And the philosophy of it. I mean, a line is not space. A line is not actually a length of time. These are philosophical concepts. So my preference is to go back and look at all the basic assumptions on these things to develop a coherent framework. And so you end up with three things: calculus, philosophy, and notation of axiomatic homogeneous infinitesimals, which is what SIPNI stands for.
Okay, well, thank you very much. I think that's been very, very helpful. And there may be some further questions coming in, which we may be able to deal with later. But if we move to the green room now, there are about 6 people in. And okay. I was just about to ask people to raise their hand. Dennis Allen has done so. So, Denny, I'm adding you to the stage. And
okay.
What point would you like to put to Jeff?
I would suggest a strategy for getting your work published.
Okay.
I would, if submitted to a mathematics journal, which is published non-standard analysis, and the title would be Another Look at Non-Standard Analysis. And the main thing is, tie it to non-standard analysis, modifying standard analysis, say, along the lines of, who was, I guess Newton was the one who first came up with the idea.
Abraham Robinson wrote the book for non-standard analysis.
Yeah, I know it, but Newton was the one who came up with the infinitesimal, wasn't he?
Yes, correct.
And so tie it to a modification of some kind of a modification of non-standard analysis in order to think of something that would be attractive.
Okay, that is actually a helpful suggestion.
I think that you'll have much better luck with that because you've tied it to something that, when I was at UC Berkeley in 1962 through 66, there was a professor there, Raphael Robinson, who published a first book on non-standard analysis, and he was very reputable. He was considered one of the stars there of the math department. And so you might submit it to an old timer in the UC Berkeley math department who would remember that, someone in logic and foundations, even though you're really aiming towards calculus,
Right.
you aren't going to get anywhere until it's published.
I agree. Is there any way you could email me even that department's name and stuff, and maybe that person's name? I agree with you, and that's what I wonder too. But I don't have. I think what you're right is I need to find an older person who is not working on current research, but is thinking about fundamental concepts and everything. I think I might be a better researcher.
It would be in the logic and foundations area of UC Berkeley math. You can bring it up in the faculty, and it gives you the pictures of them and what they work on.
Okay,
and I'm going to write someone in logic and methodology, someone older, and someone, if you could do a little searching, who has published on non-standard analysis, and so would tend to be interested, and send it to him with the right email, with the right sales email, and say a lot of prayers.
Well, that's right. How do I get my foot in the door? And I think I'm better off using the mathematical approach, like you're saying.
Yes, very definitely.
Yeah, I think as well.
Who
was this? Roberts of Berkeley, did you say?
Robinson is dead by now, I'm sure. I'm now 80. I'll be 83 in 7 days. And he was established professor then at Berkeley. And when I was went there in 1962. And I'm sure he's passed on and gone. But there are other people in the logic and foundations who he probably saw fit to hire, had them hire.
Right.
And so if you look at, it gives you a way to look up their key papers too on the website. So you'd look for something that said non-standard analysis.
So you think I would be better off going the non-standard analysis route rather than?
Yes, very definitely. Very definitely. You do not want to go the physics route. Those people are arrogant fools.
Okay. And anybody else, just to explain what Dennis is talking about, is that analysis originally was called infinitesimal analysis, but what it turned into was called real analysis, and they did away with infinitesimals. Well, back in the say again.
Weierstrass got rid of it.
Weierstrass, yes. And what happened is that infinitesimals were considered paradoxical and non-useful until the 1950s, when a certain mathematician named Abraham Robinson came out with what he called non-standard analysis, which was a way that he was thinking he would bring infinitesimals back. But it still hasn't solved a lot of stuff. You don't hear a lot about non-standard analysis in big papers or anything like that. It's niche, but there are people that study it a lot. My problem is that I have my definitions of an infinitesimal are slightly different, or not slightly, but there is a difference between what Robinson actually did. But they might be the closest mathematicians today who would understand the infinitesimal argument.
Very definitely. That's correct.
And of course, Berkeley 300 years ago had problems with infinitesimals on philosophical grounds, or even theological grounds. He said these represented the ghosts of vanished quantities, and they could be the first step to atheism. So he wrote about that.
Yes. It's got a quite interesting history. The ghost of departed quantities. I mean, there was a lot of pithy sayings about them and everything. And even if you don't like Kira, from what I do, this research, there are books called Infinitesimals, A Dangerous Concept by Amir Alexander and stuff that explain the history of this stuff. So if you're very suspect of modern mathematics and everything, I at least would recommend that you research the history of infinitesimals and stuff, just to kind of understand where we got with differential equations and all of this other stuff. How did we get to where we're at now? It is quite there's quite a rich history there.
Right. Well, I think those are very important points, and I must say I was thinking along similar lines myself. That it would be more advantageous for you in the first instance to go down the mathematical route. Is there anything else, Danny, you'd like to put to Jeff at this stage?
I wish I could think of a better title. I thought I had something, but it slipped out of my mind. I'm getting a little having senior moments now at 83. So, but I think that the advice I gave you is right. You've got to tie it to something that's being studied nowadays.
Okay.
Real and non-standard analysis is still studied at Berkeley, I believe.
Okay. I will take your advice there, Dennis.
Okay. Good luck.
Well, that's been very, very useful. So thank you very much, Danny. And if you do come up with a better suggestion for a title or something like that, you can pop it over to Jeff, and I'm sure.
Okay.
Yeah. I have, you always have things run around your head, but that's why we're all in this natural philosophy fight together, so that we can at least bounce ideas off of each other and stuff. So thank you very much.
You're welcome.
Yeah. Okay. Well, I'll remove you for the moment, Danny. If you want to come back later, there might be time. Thank you very much. Now, first of all, I'll check whether there's anybody else who has his hand up. Yes, I have two. I think I had Harry Ricker first and then Nick Percival. So I'll add Harry. Harry.
Why don't you let Nick go? Why don't you let Nick
You want Nick to go first? I think you preceded Nick. Would you like to speak?
Hi, Harry.
Hey, let Nick go.
You want Nick to go?
Yeah, bring up Nick.
Okay. I'll put you down then. You don't need to if you want.
And as always, Dennis, I'm way ahead of you.
You'd like to raise with Jeff. Go ahead, Nick.
Okay, I don't know if you got my comment. I was saying happy birthday to Dennis. Can you hear me?
Yeah, we can hear you. Happy birthday, Dennis.
Yeah.
As always, I'm way ahead of Dennis. I got to 83 months to go, for goodness sake.
Oh, well done as well.
First of all, hi, Jeff. Good to talk to you again.
Thank you, Nick.
I've been studying time for about 60 years now, and I was looking at special relativity and how to treat time, and then GPS came along, and I had the good fortune of being close talker with a close colleague with Ron Hatch, who has 30 plus patents in GPS. But looking at the GPS data, it seemed to me that motion with respect to the ECI frame was causing proper time retardation, and in particular atomic clock proper time slowing. And that led me to think that what's happening here is that the general relativity's gravitational field is acting like an ether. So we have a commonality there.
Yeah.
And I was not an etherist per se. I'm a great fan of Lorentz, but up to the point of motion with respect to some preferred frame or preferred entity causes clock slowing.
Can I ask you a question?
Sure.
So do you think that is due to a deformation of whatever is making up the clock? The definition of the waves that are making it causes the retardation?
Well,
So-
you had mentioned a perfect fluid before, so I
Yes.
was thinking of the gravitational field, and hence my version of the ether, as a perfect fluid and its motion with respect to that perfect fluid. But what the effect is when you move with respect to that perfect fluid, and in this case the gravitational field, is that you change the wave. For instance, cesium-133, I think it is, its wave, its process wave slows down.
Mhm.
And
The frequency.
the frequency that
That it vibrates at.
it vibrates at slows down. And interestingly enough, if you increase the density of the fluid, in other words, you have less gravitational potential, that also slows it down. So I think of both special relativity and general relativity as very different clock slowing phenomena, which GPS agrees with both to a very high degree of precision, really is the same effect, namely the effect of atomic processes with the gravitational field fluid. So I just thought I'd throw that out since there seemed to be a little commonality there.
So my question, so I know you studied time a lot. So you can measure time as, like, let's say the number of times a planet goes around its sun, or you can measure time as like the vibrational rate of a cesium atom. To me, the commonality I see there is that we're measuring periodic temporal events, and we're saying that's time. Would you view that as incorrect, or how would you describe it?
Well, that's really a totally different topic, which I will go into. And that is, I believe that time is not a fundamental physics construct. There is no counterpart in physical reality to time. But as you say, time has always been measured not in terms of time, but in terms of process rate. And you gave two examples, and it's always been in terms of process rate. So I don't think we should think of a coordinate system as having time as one of the fundamental coordinates. Your length, area, volume is fine. And in terms of how you would treat time, it's how energy affects processes with totally 100% within 3D space. So
Okay.
I think I'll send you my paper. I may have done it before about how I think about time as being.
Yeah, we may have had this discussion a few years back.
Yeah.
But if you can resend it to me, I would definitely read it again.
Yeah. But again, I think this is a very important foundational change to physics, because time is a what do you comes out of looking at process rates, some of which are very precise and stable, and others are varying all over the place.
Right. And to me, that's when you look philosophically at the process rate. To me, that's what the change in the magnitude of the infinitesimals are showing. Like, let's just say you have a DT. So in Sitnai, you can have DTs that are all the same, which would be philosophically equated to a cesium atom vibrating at the same rate. So one DT is the same. But if the DT is changing, the magnitude of this infinitesimal is changing, that is a geometrical representation of a philosophical change in the process rate. So that's how I equate the difference between the two. So when they say, hey, it's flat, when they say time is being flat, what they're meaning is that when they say that, geometrically, you're saying the infinitesimals are of the same magnitude. When they say there's a curvature of time, what they're actually in geometry, they're saying that the infinitesimals are changing magnitude.
Yeah.
That right, and that is, if you don't have philosophy, there's no way to understand that.
Yeah, right. And regarding GPS's atomic clocks, there are two ways that its movement with respect to the fluid, one by moving or the other going into a denser part of the fluid, produces the same result, namely clock slowing.
Okay, there's a comment in the green room by James Keene, says never been used before, and he says it's a false statement. So I would challenge James Keene to look at this equation on the left-hand side, and he is more than welcome to give me a reference to this equation on the left-hand side and send it to me. I am more than willing to debunk everything I've done if he can show me that this has ever been proposed before. So,
yeah. Well, when we finish with Nick,
okay.
I was going to bring James in so we can discuss those separately.
Sorry about that. Yeah, I'm sorry.
Yeah,
I just
no, it's all right.
But you know, all of us have our own pet theories. But I just want to make a general comment that, because I know that Jim was, making negative comments like that. But I've learned by experience. Someone made a comment to me, which I said, that's totally wrong.
Mm-hmm.
But then I said, well, let me try and understand what he's thinking. And he was looking at things from a very different perspective than I was. And when I looked at things from his perspective, a great revelation occurred. That had nothing to do with his original comment, which was wrong. But it's great that in the CNPS, we have a lot of people who are looking at things from different perspectives. And there are often things we might reject them out of hand because they don't agree with our pet theory.
Right.
But if we really take a step back and look at it from that different perspective, often an improvement to our pet theory arises.
Yeah.
So hopefully everyone will do that in terms of your presentation and your thinking.
Right. And
it's very easy to start talking at cross purposes and not getting to the nub of something. So that's very useful.
Let me just ask a question of Jeff here. Do you have your way of looking at things? Do you have to have it be in infinitesimals, or would small to large for finitesimals work? Because it seems like your perspective can be applied to the finite way of looking at things.
Well, I mean, that's a good question. I guess to answer that is that in the way I'm looking at it is that all finite line segments are made up, and it's a weird way of saying it, are made up of an infinity of infinitesimals, which is a weird thing to think. But there's this concept by Cantor, George Cantor, he's called a transfinite number. And what that means is that you can have different magnitudes of infinity, which seems like, well, why in the world would I want to have this different number of infinity? This just makes things harder. But imagine the reason is that, yes, I am saying that in this theory, a finite line, if I say a line is 10, I'm putting a real number onto a line and saying this line is a magnitude of 10. And that is to me, that's another philosophical concept, is to put real numbers onto geometry. So yes, so if I want to, I may have an infinite number of infinitesimals in a line, and I say that line is 10. But if I say I double that infinite number, I now have a value of 20. I've doubled the line. Well, this seems like a really hard way of just doubling the magnitude of a line. The problem is that if you start doing it this way, you can start doing things on a one-for-one basis that didn't make sense before. This opens up some areas of mathematics that didn't make sense before. So it seems at the beginning, it's like, why not just use a finite segment or something like that, or like a Planck length or something like that? And the reason is I want to make sure that I'm not putting an illogical concept in here just to save it. If what I'm doing is wrong, I'd like to know explicitly why is it wrong with what I'm doing. This is not anything to do really with philosophy. It's just really to do with mathematics, and it's a language that I'm saying this is what we're really doing with geometry. We just apply this to physics. And when we apply this to physics and everything, when we make these equations and everything, these gravitational constants and everything, then we're building it off of this other concept. I would like to know the root cause of why all this works. Like in engineering, you'll have equations for, hey, this is how you calculate the energy flux through a certain volume and stuff. I want to know, where did these equations come from? How did Maxwell come up with his equations and stuff? What was he thinking when he did this? What was his starting assumptions? I want to know, where did these equations come from? And what I've gone back to is that we have to go to say there's a finite line segment and it's made up of an infinite number of infinitesimals. But when we compare that with another line segment, we can compare infinities, we can compare infinitesimals. And that's all we're doing, is we're comparing them. So it's geometrical relativity. And that's what I think special and general relativity are mistaking, is that they don't understand geometrical relativity. And they're applying this to philosophy, where it's space and time.
Okay, I have two quick
Okay.
points.
Well,
one regarding, you're talking with James, and that is, I think James, when he hears the word infinitesimal, reacts and wants to dismiss it. But I think we could take your thinking and apply it to the container. Well, we could take your theory and substitute finitesimals and get a lot out of it. So I just have that message when you two converse. The other thing is, let's see if I can remember. I think a lot of confusion happens when people talk about space, and that for some people, they're talking about an abstract container only. So it's a very abstract model. Other people, when they're talking about space, they're talking, even though they may not be thinking about the contents of space. Mm-hmm. So there's a lot of reasons why people are talking at
right. They're saying the same words, but they have a different mental concept.
Exactly.
Yes.
That's it.
Okay. And that might be a bit of a contrast between classical ideas and maybe newer ideas, post-relativity, as to whether the classical idea, I suppose, would be that you need space in order for material objects to exist. But I suppose the newer idea would be that there's no space without material ideas. So it's really a bit of a chicken and egg situation.
Well, there's another way of thinking of it, is you can have infinitesimal abstract space thought of as a holder, like the bottle, whereas within the bottle, you can have just finite stuff. So there's maybe another bridge between you and Jeff.
Yeah, okay. Well, those are useful pointers for us, because we'll have a brief discussion further about some of the criticism that Jim has. So is that all, Nick, for the moment?
Yes, thank you very much, and thank you, Jeff.
And thank you for your contributions. Thank you, Nick. We'll move on now. Now, did you want to come back, Harry? Yeah. So you're back, Harry.
Okay. Well, thank you, Jeff. I think the issue here, well, my first comment and a negative comment is, I think you should have started with the end at the beginning. You end up talking about general relativity, which is your motivation, but you leave that at the end. And so I'm puzzled as to why you start off with the fundamental theorem of measurement, and then you end up talking about general relativity. But the reason you're doing this is because you have a problem with general relativity, which you don't talk about until the end.
I actually switched that slide to the end about 15 minutes before the presentation. I'm like, maybe this is too much to start out with, but I see your point, because that's what I thought. Maybe I should give my motivation for this at the beginning about why.
Okay, so here's my analysis of what you're saying. What you're saying, first off, mathematics goes back to the Greeks and Egypt and Babylonia and all this other stuff. And the idea of infinity and Zeno's paradox is already in mathematics from ancient times. So the problem is infinity. What is infinity? That's really the problem. Mathematicians haven't really figured out how to get rid of infinity. and it's a kind of a useful thing. But when you're talking about the real number system is a particular type of system of numbers in mathematics, and that has infinitesimals in it. Okay, because there's an infinite number of numbers between any two numbers in the real number system that you pick. And, and the closer you pick those two numbers to be, there's still an infinite number of numbers between them, right? Okay, this is a problem, all right? That's what this is really all about. And when the physicists try to take mathematics, which is an ideal abstract system of thought, and apply it to the real world, they just assume I can take mathematics and apply it to the real world, and the results that I get are valid. That's not really necessarily the case. That's where the problem is. So I don't think the issue here is going to be resolved by going to a math journal or correcting mathematics. The problem is correcting physics. They're making assumptions in physics based on a mathematical technique that they're using, and then they assume that it's right because math is right. Okay. I have this book here by Tipler. Okay, and he talks about the physics of immortality. I don't know if you've heard of this book. It doesn't really matter what the book's about. The point is, it's about cosmology in effect. But what he does is he's talking about physics. He says physics proves this, physics proves it. But he's not really talking about physics. He's talking about mathematics as used by physicists. Do you understand what I'm saying?
Yeah, I understand.
That's the problem. The problem is that physicists think they're doing physics when they're really doing mathematics, right? But the mathematics is not really good because it's got infinities in it. You're assuming the real number line, which has infinities in it. Okay, you've got the concept of infinity, but you can't really have that in physics. You have to have finiteness in physics, because when we make measurements, we're doing finite things. We're measuring things that are finite. Measurement is a process of doing something that's finite, right?
Well, possibly this is why modern physics has all these singularities.
Well, that's because they brought in. That's because they brought in a mathematics, which is an ideal system of logic based on these assumptions of what a number system is. So, if you assume the real numbers, then you've got infinities in there.
Well, right. Well, I guess the reason I would disagree with you, Harry, is because with mathematics, like the equation I'm showing on the screen here, this equation appears in mathematical papers, and it's over, like the left-hand side. In mathematics journals, you cannot have A equals B if I write it this way. They will say that it only can be between 0 and 1. That is.
I don't understand what you're saying. So, they're interpreting dx as being an infinitesimal, but infinitesimals really don't exist in physics. That's the point. Because I can't measure an infinitesimal. If I try to measure something, I'm going to get a number or I'm going to get 0.
Right,
but
and I'm not disagreeing with
does, presumably.
This is a geometrical language. In and of itself, it doesn't have anything to do with the real universe we find ourselves in. We're just using this as a language to describe the universe we find ourselves in.
All right, that's my point I'm getting at. Physicists have adopted this language, but it doesn't necessarily apply, and that's the whole point. The point is this philosophy of applying mathematics to physics. Does this math that we're using really apply to the physics that we're talking about?
So
that's the issue.
Right. Well, see, and I don't disagree with you there that we should be, that this is separate from what the universe we find ourselves in, what we call physics. How do we describe it? How do we quantify it? So what I'm showing here is that it's not even logically consistent just on the mathematical portion of it. So if I can break apart and show that there's flaws, that things don't equal what they say they do, just on the mathematical side, why would you believe, not why would you believe, but why would you believe the Einstein field equation? Why would you believe the way it's written there philosophically? If I could show that it can equal something else, a different value, mathematical, has nothing to do with physics, then I could say that this is actually what we're doing on the mathematical side. You're just simply philosophically equating it to things we find in our universe to quantify them. So that I don't think we are actually in disagreement. An infinitesimal is in and of itself is not an actual physical quantity or anything. We're just using this to try to say that we can measure stuff in our universe with it. To me, it's a language. It's like having an alphabet to describe snow.
Right.
You know.
Well, I don't know. I thought I've solved this problem. I presented a number of discussions on this to the cosmology discussion group, where I talk about that essentially Einstein doesn't know anything about the theory of measurement. He doesn't apply the theory of measurement to in special relativity. And what I do is I show that if you use a correct theory of measurement, you get a different mathematics than special relativity, and there's a different interpretation of it. But not many people really are much interested in this solution to the problem. I don't know whether you're interested, but it has to do with how you act. What does it mean to make a measurement in physics? And what you do is you're applying mathematics on top of a procedure of making measurements in physics. And then once they basically abstract the reality of the measurement away, and then they just talk about mathematics. So in other words, they lose track of, by abstracting the physical concepts of measurement into mathematics, you lose sight of the physicality of the measurements. That's really what the problem is.
Okay, I'll read through what you get, but I don't think that we're at odds on your definition, because like this picture here, this Riemann sum at the top here, this has nothing really to do with physics at all.
Correct.
All right, it doesn't. I mean, it has nothing actually to do with it at all. This is just simply geometry. And the bottom, you see an equation. Equation gives you economy of thought. That's what mathematical notation is for economy of thought. And you're using the notation to represent the geometry, and you're using the geometry to try to represent something physical. But that's not what it's not actually the physical entity itself. We're just using this to say that we can quantify it using this geometry. But my argument is, if we're not even doing the geometry correctly, the connotations and the philosophy of curvature of space and time is very misleading and logically flawed. So I would rather separate these things into three separate areas to say geometry is not physics. We're using this to describe the universe we find ourselves and to quantify it, but it is not the same thing as the physical reality itself.
Yes,
okay,
and
there seems to be some commonality between your views. We're going to have to wrap it up very quickly, Harry, because
all right, I just want to say one thing, and that is, in this book, The Physics of Immortality, he's a mathematical cosmologist, this guy, Frank Tipler. And I was struck by the fact that when he talks about general relativity, his view of the universe is that it's a coordinate system, as you mentioned. And I think that's the key point. I think you've hit upon the key point, and that is physicists are thinking about the world, the physical world, the universe, as a coordinate system. That's it. And the coordinate system isn't physics.
And neither is a coordinate.
It is physics. That's the problem. They think they're talking physics because they're mathematicians. They've been trained in mathematics. They're not really doing physics. They're doing mathematics and thinking they're doing physics.
Right. And I agree with you. They think of, hey, as if we're going to place this coordinate system and use this to describe our universe and everything, that when you get into that mindset and you think coordinate system, well, how do I add, if I have a three-dimensional coordinate system and I want to add a fourth dimension, well, that's a fourth coordinate system. And you start applying where these points start changing and stuff. And you're like, oh, well, that's how our universe is working, is we're changing this coordinate system. But the problem is that's not really what the equations show. That's not what it was derived from. It's derived from, to me, what is a point? What do you say a point in space is and everything? And you say, well, how far a distance is a point? The problem is that you are taking a geometrical argument and applying that to our physical universe by saying I can have a points here on a piece of paper and I can tell the difference between them, and I can say I have points here in our physical universe. It's like, do I have 2 points with a distance between them, or do I have one infinitesimal? To me, that's a geometrical argument, a philosophical geometrical, and we're applying that to our real to our universe and describing how it works. They are not the same. The universe, when you start saying you lock it in, say this is a coordinate system and this is what we're doing, this is what we're changing everything, you have locked yourself philosophically into this, that you have to solve everything with changing this coordinate system. But the problem is that general relativity says it changes coordinate systems locally. Well, what do you do when your coordinate system universe-wide starts changing distances? Well, we need something to change the distance universe-wide. We're going to bring in a perfect fluid again that changes density. To me, that
I'm sorry to rush this on a bit, but I do want to bring James Keenan because he's made a number of critical comments, which are very welcome, but I'd like to deal with those. So, if you gentlemen would like to continue this conversation.
Well, I'd like to invite Jeff to participate in the cosmology discussion group that we have on Sundays at 10. So
I would love to, but I'm getting ready to fly tomorrow. And but I always go back and I look at what I can on YouTube.
All right.
Okay, they're all recorded, yes.
Thank you, Harry.
Okay, well, thank you very much, Harry, for that. That's a very interesting discussion. And just before we get to Jim, there's just one question here. I don't know, but he's saying, question for Jim. Eventually, this unique view has to collapse back into standard math. So, under what rule are two infinitesimals the same? I don't know if in a word or two you can dispel.
Yeah. So how do you know that two infinitesimal are the same? That is an abstract concept. It's the same thing as, well, here I'll show you. If we go to dy over dx, I'll show you the differences between the two. Okay. In regular math, and especially in Leibniz notation, dy over dx is the rise over run, right? In Sitnai, dy and dx are the same. So dy over dx equals 1. If you have a value that is not 1, then they are not the same. If you're just measuring two infinitesimals relative to each other. So that was what I mean by the same. You would define that as the same as either these equal 1, or if you subtract the magnitudes against each other, you would have 0. That's how you define them as being the same. They have no absolute magnitude of themselves. It's just, are they the same magnitudes? That's how you would define whether or not they're the same.
Definition, yeah. He just goes on.
But when you look at what a derivative is of a function and everything, you're actually measuring the height difference on two columns. You have a change in the number of elements, the number of height. You're not actually looking at dy over dx. You're looking at the change in the height of them. That is I think to me is a pretty telling distinction between Sitnai and Leibniz's notation. This here, if you do it this method where you're using columns of elements of area, and remember they don't have any corners to them any more than a what do you call it? A Riemann sum. When you take a Riemann sum and you make these smaller and smaller till they equal the slope of these line here, it's the same thing. This you're looking at the same thing three different ways here. On the left is how mainstream mathematics would look at it, and on the right is how Sitnai would look at it. But this has, in and of itself, has nothing to do with physics. This could be the change in the number of people that entered a gate. Okay, you can use calculus to find the rate of the number of people coming through the gate. That has nothing to do with physics. This is just a language for describing infinitesimal changes. And I'm just going back to the very basics beginning of it. Sorry about that. So when James, or who was it that wrote that? I'm sorry.
Well, I'd have to go back to the comments now. It's where it is now.
Oh, he was asking about how do I define infinitesimals being of the same magnitude? Is whether their ratio equals 1. Yeah.
Okay. By the way, you've probably seen Jeff and others that Dennis Allen has suggested something like a new approach to non-standard analysis.
As a title, yes, I saw that. Communicating
with the mathematics people. Now, if this is all right, Jeff and everybody else, I would like to bring James Keenan because he's made a number of comments here, rather critical or so on, but they're very welcome. But I'd like to ask you, Jim, because we haven't had an opportunity of going through the comments in detail. They're just sent from the green room comments. So if you'd like to highlight some of your major problems or your major criticisms, or maybe even contrasting how your ideas within binary mechanics fit or don't fit with Jeff's ideas, please feel free to do so. We don't have long to deal with it.
Yeah, just briefly, whether my comments are actually criticisms or just questions about aspects of Jeff's talk, and thank you, Jeff, for getting your talk today. Why don't we just focus on this comment, never used before, which is the slide that you're looking at right now on the left.
Yep.
You said that's never been used before.
That is correct.
Well, gee, I have 2 points about that. One is some 100 papers on my website, which is a free online journal, which claims to use that.
Okay.
So in the future, you can either cite that or explain perhaps in an email to me or whatever, why you're saying that it's never been used before when going back well over a decade, these papers have used this routinely. The second example, I realize you can't respond to that right now, but that's why I say never used before is a false statement. The second point with regard to never used before is on my property. I do some carpentry and construction work and use a tape measure. And I routinely make measurements and express them in the units dx, where dx is feet, and I talk about the number of feet. And so in doing that construction, whether it's me using the tape measure or carpenters or constructors that I hire, they all seem to be using your equation, not only for length, but also for computing areas and volumes. And yet you say it's never been used before, but I have carpenters and construction people working for me who have never even graduated high school, who use it every day.
I would have to look at what it is you're talking about, because, I've had advanced calculus and everything, and I'm an engineer myself, so I'm not sure exactly what you mean. I would be more than willing to look through it.
Okay, I have a 2x4, and
Yeah.
I place my tape measure down, and I read a number off the tape measure which says 10. So that 2x4 is 10 times dx, where the dx is 1 foot. And I'm using your equation on the left that you claim has never been used before.
Okay, I understand what you're saying now.
I think that's a false statement.
Right. So this is a great philosophical distinction between what you're saying and what I'm saying here, is that, and this is how engineers, how construction people think and stuff, is that what he's saying is that if I have the dx here, like what I'm showing here, and I have a dy, well, I can just measure this and calculate how much area there is, right? I can take a square or rectangle and measure both sides, multiply those together.
That's not what the carpenter is using. He's using a tape measure, which is either in meters or feet. Some folks here have their tape measures show me meters. It doesn't matter.
Right. And
but that's your dx. There is no dy.
Right. Oh, but if you were going to measure area,
I don't know what you're trying to say here, and yet you're denying that ordinary carpenters making measurements of length, area, and volume, which they routinely do using a tape measure,
right, using only length,
that what you're saying is never used before, and yet these folks use it every day.
These are finite elements.
That's fine. This is the hard part of understanding here. The distinction is that he's saying they're using a tape measure to measure length all the time, and he's saying there's no dy. But if you have a piece of plywood, it's a 4x8 piece of plywood, and I need to know how much area does this piece of plywood cover if I cut it up in many different pieces. You might have different areas I need to know. You're going to measure, you're going to figure out, even like if you roof a house, and you need to know how many squares are going on the roof, you're not measuring the length of the squares. You're measuring how much area am I going to need to cover the roof of this house. All right. So you need to know how much total area do I have. And with a tape measure, I can just measure one side and the other side, and I can figure out how much area is in a square of shingles and stuff. The distinction here is that with this, you are actually not looking at an infinitesimal measurement on one side and an infinitesimal measurement on the other side. You're looking at in specific elements of area in each one, and you're counting up the total number. Now, why would you even care? Why would you even care? Why would you even want to bother doing it this way if it just makes it harder? And this is why it's never been done before. Why would you care to do that when it makes it harder? The reason is
do
because
what? I thought you just said.
Why would you want to measure in elements of area instead of two elements of length? All right, that's if I'm measuring area. You say, well, I have a 2x4 and everything. A 2x4 itself has dimensions and stuff. You can't just take a stick of no width and everything and use it to build a house with. You have to have volume with the stick and stuff. What I'm telling you is that is the way we think, is we take elements of length, another element of length and everything, and we use those to calculate how much area we have.
But my carpenters, they only have one tape measure, and they're only using one element of length.
But they're using elements of length to make area.
And they don't care about the...
We're going to have to terminate the conversation now.
Okay.
I'm sorry, Jim.
Yeah, I don't think you're addressing the question. That's my conclusion.
Okay, well,
okay, I'm done.
Take this offline.
Apparently, Jeff cannot answer the question.
Okay.
That's my conclusion.
Well, I've cut him off. I hope I'm not responsible. I'd really like to give Jeff an opportunity of summarizing. Thank you, Jim, for the moment anyway. I'd like to give Jeff the opportunity of summarizing the talk and the comments and indeed the discussion. He might even want to say a word or two about what Jim says you're not addressing. I'd like to give him up to 5 minutes to do that. And I think it would be quite unfortunate if we didn't have an opportunity to do that. So sorry for terminating the question and answer session. But I think actually the fact that this could have gone on for long more is indicative of the interest that the very fundamental points that Jeff raises has spurred on. So Jeff, I'm going to give you the floor for up to 5 minutes to summarize anything that we left hanging, that I cut people off, I cut you off maybe on, you might want to address very, very briefly, and then I'll come back and close the meeting officially. Okay.
Okay. Thanks, Ian.
So Jeff, the floor is all yours now. Shall I bring down your slides this time?
No, I'd like to have the slides still up there. Okay. So basically, as I was asked, what was the motivation for all this? Why bother with all this? Why bother with the mathematics and stuff? So the question came out of general relativity. There's this cosmological constant problem, and you can read about it and everything. It's considered the worst problem in physics. And forget about natural philosophy, forget about everything else. Where did this problem come from? That's what I want to know, is that if you break this down as much as you possibly can, down to the most basic level of between what mainstream mathematics is saying about it and mainstream physics and everything. What's nice about it is that we kind of live in a time where our observations get better and better, and we now see that our universe does not obey the laws of physics as what we're being told. So that's what this motivation behind this is to break it down, reverse engineer it down to the most basic level. And when you do that, this cosmological constant, this lambda, is multiplied as a scale factor against this thing called G mu nu, which is actually is just a scale factor itself. And what you don't hear the physicists or the mathematicians saying is that you multiply this by these dx's, right? And which I would call an infinitesimal. And there's a reason why there's two of them there. So, but if you break it down, all you're looking at is scale factors times an infinitesimal. Well, I understand that this is mathematics, and this is not the physical world we find ourselves in. This is like a language. And so that's all I'm doing is reverse engineering general relativity to find out what this problem, where did it start at? And as I've taken all of these different things and started coalescing into one thing, this SIPNI, is that you start to also look at how, as a people, as a species, do we measure things? Like James was talking about with a tape measure and stuff. He says, well, I have one tape measure and I use that just to measure. But you use a tape measure, you can measure it one direction one way and another direction another way, and you can calculate area. You can calculate volumes. And these are finite measurements as we view them. So why would you want to have anything else this more complicated way? The reason you would want to take this more complicated way is that when you have these tools available to you, these more complicated way, and you start changing them, they start to look like what mainstream physics is saying about curvature of space and time. All these things you're told here start to look like what these are over here. They seem to have the same properties. And as you develop it more and more, you start to see all these same properties. You start to say, well, how do I know that they're not mistaking this for this? But if you're not willing to say, this is the most fundamental way of writing this, even though it's harder in the beginning, if it's not harder, you don't have these options to change. So that is the point of me doing this, is to try to solve this issue of how do we write these things down to describe the universe we find ourselves in. So that is what led me to reverse engineer general relativity, which required reverse engineering Euclidean, non-Euclidean geometry, and reverse engineering the development of calculus and stuff, to see that we're doing things in a backwards way. But you also have to deal with what James Keen is talking about, is we physically think of a tape measure, we think of length, and I think of this as volume and stuff. You have to look at it a different way. And then this involves something called set theory, where I'm saying I have a certain number of elements in this set, and I'm saying the magnitudes are equal if the ratio of them are equal, or I can say the cardinality of these two sets are equal. And if the magnitude is equal, then they're the same finite length. Well, you say, well, how is it a finite length? Well, I determine what a length of a line is. You know, you can say it's a foot. Somebody else can say it's a meter. Somebody else can say it's a cubit. You know, we have all these different ways of what we call a length here, but we know that length, I say we know, most people accept that there are some type of length contractions and some type of vibrational changes and stuff to time and everything. That's all this is I'm trying to see whether or not these infinitesimals, if they change magnitude and cardinality thing, can instead describe what we're seeing here, and that this is a more coherent language. So that is the basis of my whole research. Thank you, Ian.
Well, thank you very much, Jeff. And I'll take the stage to myself, if I may now, just to complete the session. Unfortunately, we've run out of time, but in a way, that's a good sign. It indicates, in no uncertain terms, the interest that has arisen from your exposition. And I'll be very brief because we've actually just run out of time. But I think Jeff has given some very deep thought to this whole system of SIPNI. And it's interesting actually how he has specified how the whole process has been one of reverse engineering. Now, we who are basically dealing with what was generally fundamentally called natural philosophy would be extremely interested to hear that he started with reverse engineering general relativity because there seemed something wrong with it. And that led on to his reversing or reverse engineering the whole of fundamental mathematical theory. And it's resulted in this area where we've tried to discuss whether he should be inputting his ideas as a fundamental reassessment of mathematical techniques, or whether he should be including in that or even emphasizing the application to modern physics. And I think he needs to concentrate in both areas. He shouldn't neglect both, because he's got a lot of interesting things to say, both from the point of view of mathematics and also from its application to physics. So it falls upon me to thank Jeff very much. I think this is the third time he's come within about 18 months to give us the benefit in the CNPS of his research. And somebody here said he was a clear speaker. Others said they couldn't understand a word that he was saying of the mathematics, but others said he was a clear speaker. So thank you very much for that. Thank you, Jeff, for your patience in making out all these detailed slides and dealing with the questions and so on. And actually, I think there'll be a possibility of continuing some of these discussions with Harry, maybe in the cosmology group, and with Jim, maybe offline, and so on. So I must end the proceedings now. I'd like to thank you all in the social media for all your questions. I see that the half dozen or more of questions that have come in on the social media. We didn't have time to deal with them. I'm sorry. Maybe we'll come back to them at a later stage. And thank you all in the green room for participating. All your comments are very, very valuable. They were a help to us, and I hope there'll be some help to Jeff. We always like to repay our speaker in ever so slight a way, if possible, for the work that has gone into giving us the talk. And if it's been useful, if Dennis's pointers and so on to the mathematics people have been useful, well, we'll have repaid Jeff, if in ever so small a way. So I'd like to thank you all again, and thank you very much, last but not least, our speaker, for the trouble he's gone to in giving us this very clear and detailed exposition. I hope to hear more from him and also from the rest of you. So I'm going to end the stream now and wish you all, wherever you are, a very good day.